Okay, in this video we're going to be starting our discussion about 2D kinematics. So in the previous set of videos we finished up our discussion on 1D kinematics. We developed a number of equations, and we're now able to solve problems in 1D kinematics. Now what we want to do is we want to ramp this up to being able to answer problems about objects moving in 2 dimensions. Okay, and we're going to find that we can do this by simply breaking up the problem into two one-dimensional problems. It's going to end up being two coupled one-dimensional problems. And once we've broken up the problem, then we can just apply all the same tools we used in the previous chapter to solve the problem. Okay, but before we're able to really jump into this, we need to develop some more tools to help us sort of break up some of these two-dimensional quantities in such a way that we can answer questions by breaking the question up into two one-dimensional problems, right? Okay, so we're going to start off with a little bit of a discussion on vectors in 2 dimensions. So if you remember from our last video series, we looked at the difference between scalars and vectors. We looked at all these quantities in the context of our 1D kinematics discussion, and we found that these were all the quantities that were vectors, and these were all the scalars that we talked about. So for example, position and displacement, velocity, acceleration, these were all vectors. And so in one dimension, and we can imagine that we're on some sort of a one-dimensional line here, let's say this is our x-axis, and so our position, let's say, or maybe we'll talk about velocity. Let's say we had a velocity. We could have a velocity pointing in this direction, and it could have a magnitude of 1, and it would be positive. It's pointing in that direction. Or if it was pointing in this direction and it had the same magnitude, it would be sort of negative, right? And so in one dimension, all of our vectors were either positive or negative, and that's all they could really be. Positive and negative was enough to describe magnitude and the facing of the vector, right? But now, if we ramp this problem up to 2D, we can see we run into a bit of a problem, right? So let's imagine we have our Cartesian coordinates here. Let's call it our x-axis and our y-axis. So this would be, like, we could still think about things in one dimension. Again, if we had something that was only out along the x-axis here, we could describe it with only a plus or a minus in the x direction, right? So this would be something like x equals 2 or something, right? This point here. But we can also now have things that combine the two. Let's imagine we had some vector pointing out. And when I say vector here, I just mean some quantity that has both a magnitude and a direction. The direction doesn't have to point along one of these axes. So in this case, let me just get rid of this. In this case here, let's call this vector A. And this is how I'm going to write vectors from now on. I'm going to write vectors with this little arrow over top. Maybe a quick note on notation. Vectors will either be written in your text as a sort of bold letter, like this, or if you write it by hand, or in some text, you'll find vectors written with a little arrow over top. And this just means vector. So this is indicating to you that this is a quantity with magnitude and direction. Okay. Whereas if you just see a symbol like this, just a regular letter, this is telling you that this is a scalar. And if you see the same letter used, and we're talking about, let's say we see a vector A, then we can say that the magnitude of that vector A can just be written as the scalar A. Okay? And so in this case, let's go back to our Cartesian coordinates over here. Here we have our vector A, and our vector A doesn't just point in the x or y direction, right? It points a little bit in the x direction and a little bit in the y direction. And so we need some way of breaking this vector up into its x component and its y component so that we can apply all of the one-dimensional tools that we developed in the previous chapter, right? And so generally speaking, we're going to find that these vectors that we're dealing with are going to be velocity vectors. But I'm just going to leave it some general vector, some vector A here. It doesn't have to be a velocity. It could be a position, a displacement. It could be anything, really. It doesn't have to be something physical at all. But we need some way of being able to translate this vector from pointing out into the plane here into its components. So let's start off by labeling this vector. Let's call this angle in here theta. Okay, I'm going to call this theta A. And the length of the vector, which is just its magnitude, we're going to call that A, right? So this is the same idea that we have down here. We have the vector, and then we have the magnitude of the vector, which is just A, right? So we have our vector here, and we have the magnitude of that vector here, right? And this angle in here is just telling us the direction in which that magnitude is pointing, right? So if we put some numbers to this, let's say A is equal to 5 meters. So if I do it this way, that means that A is a position vector. The vector A is a position vector. And if we have our theta A, let's give that a value of, say, 36.87 degrees. Okay. So we have our vector pointing out into the plane, and we would like to find a way to be able to translate this vector, which is written in the form of a magnitude and an angle, into its two components. So we want to be able to break it up into two vectors which point one along the x direction and one along the y direction. Okay, and that's sort of the whole goal of this, because once we've done that, once we have velocities or whatever quantity we want, whatever kinematic quantity that we've already talked about in the previous chapter, pointing along these directions, then we've basically broken the problem up into two separate problems, and we can use all these tools that we developed to solve this, right? So how would we go about doing this? Well, we can see right away, and maybe I'm going to redraw this below so we have a little more space to work. Let's put it here, let's say. And so again, x, y, our vector A with magnitude A and angle theta A, where we've said that A is 5 meters and theta A is 36.87 degrees. Okay, so right away we can kind of see how we could do this. We just think about trigonometry, right? We can imagine just dropping a vertical down this way. This is going to be a right angle here. And then right away from well, whatever mnemonic you use, but I use SOHCAHTOA, we can see that the sine of this angle, so this is telling us that the sine of theta A is going to be equal to the magnitude of our vector AY. And so I'm going to define those in a second, but let's be careful here. So this bottom quantity, this magnitude of the vector A, well, that's just A. This is just A that we're talking about here, right? This is actually equal to the magnitude of A. So when we have this denominator here, we're just saying that with the denominator in the basement, this is going to give us the magnitude of AY. Well, AY is just this distance here, but that again can just be mapped onto our y coordinate here, and so AY, the vector, is just a vector that points along the y-axis with a magnitude equal to whatever this quantity here in this equation is that we need to solve the problem. So in this case, let's say, for example, we would end up with a sine of 36.87 degrees is equal to something over 5, right? And this is our AY. And again, I'm just going to write interchangeably. If I write this, that's the same as writing that, right? We're just talking about the magnitude of that AY vector, which is pointing in the positive y direction, right? And so we can simply rearrange this. If we move the 5 over, we're going to find that AY has a magnitude of 3 meters. Okay? And we know that AY always points in the y direction. So this is the scalar, this is the magnitude AY, but this is the vector AY. This one has information about direction and magnitude, whereas this one over here only has information about magnitude. But they're really telling us the same thing here, because AY is always going to point in the y direction. Okay. We can do a very similar thing now with cosine, and well, I'll write it out here, I guess. This is going to lead us to see what the x component here is. So we're going to find this ax, or at least we're going to find the magnitude of ax, right? And so if we do that, we can again reorganize this. In that way, and if we substitute in numbers, and I won't do the full substitution, but if you do, you simply slide in the 5 there and the angle there, and we come up with our magnitude for ax, and we're going to find that ax is 4 meters. And so in this case, these numbers won't always work out so nicely. I selected this a up here to be 5, and the angle such that it's going to end up giving us a Pythagorean triple, right? So this is just a 3, 4, 5 triangle. Generally speaking, these numbers won't always work out to be whole numbers. It could be whatever, depending on what the angle is, right? But we've sort of discovered a tool that's going to help us, convert from these vectors written in terms of their magnitude at an angle from the x-axis into a way that they're written such that we can break them up into 2 parts. So for example, let's say we had a vector, we have some vector A. This vector could be written in the following form. It could be some magnitude A at some angle theta A, right? So we have 5 meters pointing at 36.87 degrees. And now what we've done is we've found a way to translate this into a vector A that's written as the sum of 2 vectors. So let's take a look at this here, and we're going to take a look at this sort of in a graphical sense in a second, but it's now written in the form of 2 vectors which are added together, right? So we've gone from writing the vector as some magnitude in some direction to the sum of 2 vectors which point in directions that we know about, in the x direction and in the y direction. And we can see that this is true because if we were to come back up to here, and I'm going to change colors, if we were to come back up to here and we took this ax and this ay and we added them tail to head, we could first follow along the ax vector to here, and if we slid this ay over, we would see that the ay adds up in this way and brings us right back to the point that our original vector A was indicating to us, right? So really what we have here is a way to translate from a vector written in this way to a vector written in this way, where this is the way we need a vector written to be able to break the problem up. Because now we just take the ax part and the ay part, and we have 2 separate problems, one in the x direction and one in the y direction. And this is how we're going to solve these problems. We're going to break the problem up, solve the x direction problem, and then solve the y direction problem. And the thing that's going to be shared between the 2 is the time. So we're often going to use time to translate between what's happening in the x direction and what's happening in the y direction. Now I know right now this probably seems a little bit abstract, but when we get into it and these vectors become velocity vectors and we're talking about projectile problems, it's going to become more clear. So for now, let's just keep developing this idea of vectors and this sort of set of tools that allows us to translate between the vectors written in one way and written the other way, and then we're going to see how we're going to use them in a problem afterward. Okay. We also need to have a sort of notion of how vectors are going to add and subtract right over here. And I'm going to go back through later on and clean up these notes a little bit because there's a lot of scribbling here. But we can see here that basically what we're talking about is adding two vectors. Whenever we're adding vectors, we have to be careful that we're only adding vectors to other vectors or scalars to other scalars, right? So if we're adding two numbers, we can add 5 plus 3, and that gives us 8. And we can add two vectors, a plus b, and if there's some vectors on some sort of a 2D plane, let's say this is a and this is b, we could add those together just by adding them head to tail, and this would give us, this is also b, let's say, this will give us some vector, and again I'm making a bit of a mess here, but this will give us some vector like this, which is the vector, we'll call this c. C is equal to a plus b, right? And so the sort of idea of adding them up as pictures is something we should always have in our heads, right? We're adding our vectors up head to tail, and we want to be able to do this algebraically, which will allow us to break up these vectors in such a way that we can solve the problems. Okay. And so let's go back to our original problem here. And let's say instead we were given the vector in this form, in the form of our vector broken up into an x and y component, and we wanted to go back into this form over here, right? So how would we do that? Well, again, Pythagoras can kind of guide us. If we have this ax magnitude, and we have the ay, let's think of ay as being over here, and this is some sort of a triangle, right? That we're looking at, then clearly the sum of the square of the two sides which are hitting our right angle are going to give us the square of the hypotenuse. And so if we want, written in terms of the variables we have here, if we want a being the magnitude of our vector a here, all we need is to take the square root of ax squared plus ay squared, right? And just going back to our drawing up here, we can see that that's just going to be the magnitude of this value squared and the magnitude of ay here, right, squared. And then take the square root, obviously, right? And if we wanted to find the angle, in here, well, we could easily get that from the tan relationship here, right? So we just need the inverse of tan because we know that tan theta is just going to be equal to ay over ax here. Oops, and that should be an x. There we go. Right, because we have opposite over adjacent, right? So ay over ax. So if we rearrange that, that's just going to give us the following here. We're going to find that our theta a is equal to tan to the minus 1 ay over ax. Okay, and so with this equation, and I'm going to collect them down below so you guys have a sort of nice way to think about it. And these two equations in here, we're going to find that we have all the tools that we need to go from this way of writing the vector into this way of writing it. And so I'm going to kind of write down the punchline down here. I have it on this paper over here. And we can sort of think about it in these terms. Let's say we're given a vector written in the form of a magnitude at some sort of direction theta a. So we're talking about the vector theta has magnitude a and it points in direction theta a. If we then want to go to the vector a written in terms of a vector ax plus a vector ay, where ax and ay point in the x and y directions, then to get from here to here, we're going to go through these equations. Ax is equal to a cos theta a, and ay is equal to a sine theta a. Okay, and these equations will give us, will bring us from the top representation of the vector down to the bottom one, right? So we start here, let's say. We simply feed in the magnitude and the angle into this equation here, and we get our magnitudes of the vector components coming out over here, and we get our vector written this way. And this is the way we want it to be able to work with the equations that we have generated already. Let's say afterward we're asked to rewrite this in terms of a magnitude and direction. Well, that's fine. To go back up this way, we can always get the magnitude A back from Pythagoras with ax squared plus ay squared. And if we want that angle, theta A, that's just tan to the minus 1 ay over ax. Okay, and that'll get us back here. And this is really the punchline of this first video here. We just need to know how to be able to go from vectors written one way into the other way so that we can then apply the tools that we've already worked on to solve this problem, right? And we're going to look at some examples soon. Before we move on, and this is sort of a key takeaway thing here, so I'm going to put a box around it, and you want to remember how to do this. Before we move on, I'm just going to quickly talk a little bit about the addition of vectors, subtraction of vectors, and the multiplication of vectors by scalars. Okay, and we're going to talk about that quickly. Oops. There we go. Okay, so vector addition and subtraction. This may be the first thing to talk about. So, as I drew very quickly above, we can think about the addition of vectors or the subtraction of vectors in the following way. So imagine we have some, and it doesn't matter what the actual numbers are here, but imagine we have some vector A and some vector B here. Let's say we wanted to add these vectors. Well, we should always imagine doing these sort of in, like pictorially, as follows. We imagine adding A to B by sliding the vector B up A such that it points this way, right? You can imagine just sliding this up until the tail hits the head of A, and then whatever this is here, this is going to give us some vector, which above I called C, where C is equal to A plus B, right? And so, could we do this algebraically? Well, we could for sure. And so let's say we were given some values here. Let's say we had this angle in here and this angle in here, and this was theta A and this one was theta B, and we had some magnitude A and some magnitude B, right? So we would have A written like this, and B written in this way. Right? And it would be a little tricky to add these up because you'd have to be doing a bunch of trigonometry. You'd have to find out where the point that A pointed was at, and then build another triangle off of that. But there's a much easier way. If we want to add these together, we simply use the tools that we set up here. We simply use these equations here to translate these into their component forms. So we can rewrite A as some AX plus AY, and B as some BX plus BY. And once we've done that, then the addition is simple. Then we just add up the components. So then we just add up the X components and the Y components, and we're going to find that we end up with the right answer. So we basically take AX plus that should be a B, BX, and this is going to give us CX. right? And we can kind of see that from the plot here. We can imagine if we broke up the x component of A and the x component of B, and we added them together, we would end up somewhere out here, right? So this is AX, this is BX, and if we add them up together, we end up out here, and this is CX. And the same is true for the y components, right? If we added, say this is AY, or yeah, AY, and then this in here would be a little by. If we added those together, if we shifted this up onto the top here, we would end up with some cy, and if I had drawn this correctly, that would kind of match up to that point there. So again, so we end up with, going back over to the algebraic side over here, we end up with some AY plus BY equals CY. And then using these two components here, this gives us our C, which is equal to CX plus CY, right? And so that's kind of how we would handle the addition. The subtraction would work the same way, except that we would then think of our vector B. Let's say we wanted some vector D equal to A minus B, right? Then we would simply think of the B vector pointing in the opposite direction, or let's use a different color. So let's imagine the B vector is now negative B. So negative B is just going to be the B vector pointing this way, and that's just negative B. And you can do the same argument here sort of pictorially, but in the end you just end up flipping these minus signs in here, or what are plus signs now, into minus signs, and you end up with your dx, which is going to be equal to ax minus bx, and your dy, which is going to be equal to ay minus dy. Minus by, sorry. Okay, and that's sort of just a quick look at how to add these up. We will look at more sort of firm examples, but you can sort of think of this both ways. That's kind of the point of this. You can kind of think of it as this drawing on this side here, where you're adding them up, the vectors head to tail, or you can think of it algebraically, which is the way you're actually going to have to work with them by breaking these vectors up, right? And so finally, the last thing I want to talk about is the multiplication of vectors by scalars. And we're not going to use this too much in this course, but we should know how to do it. Let's say we had some vector A, right? And let's say this vector was written in this form, or equivalently, we could have the vector written like this. And we now wanted to multiply it by some scalar. Say the lowercase a is some scalar. So what is a? Well, in the case of the first representation of our vector here, this one, we can simply say that AA is just AA at theta A. So it's basically just taking the vector. Imagine again the vector in the plane. Say this is A, and let's say the magnitude of A is I don't know, 5 meters, and let's say A is just some scalar. It's just 2, let's say, right? So then the vector made by A multiplying uppercase A, maybe that was a poor choice of letters because it's making it more confusing, but you can imagine that, that this would be AA, which is just 2A, right? It's just multiplying the magnitude of the vector in that direction. The same idea is going to work with this representation of of the vector, we're just going to end up with AA is just equal to AX plus AY. So it kind of just distributes as though it was just a regular number, right? As though it was just a scalar. You can think of this like, and maybe this is going to make it worse, but let's try it like this. You can imagine that A is just some B plus C, where they're just regular numbers. If you wanted to multiply by some A, well, you would end up with this equation here, right? And so the same idea applies here. You're just distributing that scalar over the two vectors, and it's going to again give you the same result. You can imagine down here if you had AX and you multiplied it by 2, well, you'd end up, again, if I had drawn it correctly, you'd end up somewhere here. And again, AY, if you multiplied it by 2, you would end up over here, right? So the scalar multiplication, like the multiplying a vector by a scalar is done in this way. And as I said, we're not going to use this a lot in this course, but it's useful to see it at least once. Would be handled sort of in this way. And the addition or subtraction of vectors would be handled in this way. So this was a lot of sort of theory on vectors. Some of it's going to be more useful than other parts. I wouldn't worry too much if not all of it was super clear to you right now. The takeaway message for this video is definitely this set of equations here. You're definitely going to need to know how to go from vectors written in the top form to the bottom form here, written in terms of their magnitude and their angle, into their components and back. So this is really the key takeaway from this video. And in the next video, we're going to take a look at some examples, and then move into the actual 2D kinematics problems where we're going to apply these ideas of vectors. Okay.